Now, here's another way we can implement the stack ADT based on lists, but this time using the front of the list to represent the top of the stack. So stack number 2 looks pretty much the same at the beginning. Items is still a new list. We just see if that's the same for our is empty. When we push, we insert at index 0. And when we pop from index 0. In other words, making the front of the list our new top, quote unquote. And we got our error raising here. Even though this implementation looks basically the same as the other one, not too significant of changes here. Insert instead of append. Pop just has an index now. Turns out the actual time that it takes to run these is quite different. By using a built-in Python library called timeit, we can get a rough estimate on how long it takes our code to run. The function we import is called timeit, which is the same as the library. This is pretty common. Which takes in a piece of Python code to execute and returns a float representing the amount of time it took to execute it. So we can use it in the following example. Here's a method called push and pop. It pushes and pops a single item. This just helps us for timing. So we import our timeit. We get stack sizes of 1,000, 10,000, 100,000, million, 10 million. And for each of those stack sizes, we're going to make a new stack. We're going to skip past the stack interface to create a stack of this size. This is going to speed up our experiment, but this is obviously bad practice. You shouldn't actually be doing this. And we're going to call push and pop stack 1,000 times and store the time that it takes in this variable. Over here you see there's a thing that says globals equals globals. This is just a technical thing, don't worry about it. Finally, report the result. Here you can see there's a weird pointy smiley face, colon greater than 8. This is just to right align the stack size when it's printed, which makes our report look a little nicer. Running this code on a stack and a stack 2 instance illustrates a very big difference between these classes. Let's actually see if I can just run this. I should be able to, right? Push and pop. Yeah, let's give it a shot. Why not? Okay, here. Whoop. I think I have to grab the stack 2 code as well. And let's see if this works. Okay, tried it, didn't work on Python Tutor. We're just gonna run it on my computer because sadly it didn't work. Okay, let's try this out. Get some times here. Cool and good. Now let's try it with the other version. So bear in mind what we've seen so far is the original storing everything at the end of the list using append and pop. That's it. Stack number 2, this is our storing everything at the beginning of the list. Now code-wise, they look really similar, right? Yeah. Ugh, indentation problems. Whoa! So this one, 0.0004 time. This one, ludicrously long in comparison, right? We had to actually sit here. While you were watching this video, it hadn't finished doing the 10 million one. It still was going. I think that was, 7 seconds is what this is timing, I'm pretty sure. That's astronomically bigger than these ones. So there is a concern with regards to the, let me open it up again. The time that it takes to run this stuff. Yep. Well, the stack instance itself seems to take the same amount of time per operation regardless of how many items are on the stack. Stack 2 seems to have the amount of time grow with the number of items on the stack. In fact, the amount of time required for stack 2 is roughly proportional to the size of the stack, while the time that it took to do the first stack was independent of the size of the stack. So to understand why there was such a dramatic difference, the amount of time it took, we need to understand how Python lists are stored in memory. So remember, variables in Python store references to objects. A Python list is a special type of object that contains an ordered sequence of references to other objects, which we call the elements. Importantly, these references are stored in consecutive blocks of memory, just like we've been drawing in those memory diagrams we've been seeing. This is what makes accessing something in a list so fast. Getting the ith element of a list can be done by just calculating what the address is based on where it starts and like offset by I addresses. So the quick note here, think about it like this. Suppose you're walking down a hallway with number of rooms on one side, and room numbers are going up by 1. If you see the first room number is 11 and you're looking for room 15, you don't have to count every room you're going through. You can just say, oh, it's the 5th room down the hall. You don't have to look at every room number on your way. To preserve this characteristic, lists must always be contiguous. There can't be any gaps, otherwise you won't be able to calculate the memory address of the ith list item. But this makes insertion and deletion less efficient. In order to delete an item, everything after it has to be moved down 1 block in memory. Similarly, for insertion, all items are moved up 1 block. So we have a trade-off. We give up fast insertion and deletion in order to get fast lookup by index. There's one more important feature of Python lists you should know, and it makes adding elements to the end of a list very fast. When you make a new list in Python, it actually allocates more memory to the list than what is actually required. If you make a list of 4 elements, you actually might get enough space to hold 8. The exact numbers are implementation specific, not really important. The general idea, though, is that there is usually free space at the end of the list that the list can expand into. So if you want to add a new item to the end of the list, you can simply add a reference to it in that spot. On the other hand, if you want to add something to the list and there is no more free space, a new and larger chunk of memory is allocated for the list and everything is copied over. This is something you'll see in a lot more detail, in particular for CSC148, but this is something that you're going to need to know just in terms of understanding how a list works. The net effect of these little details is that it's much, much faster to add and remove to the end of a list than to the front. If you add to the end, very often you're just expanding into the extra space that's there. Sometimes there won't be any extra space left, and you do need to do some annoying stuff to make sure there's enough room for everything to fit. But on balance, adding to the end is much less time consuming than adding to the beginning, because if you add to the beginning, you always have to shift everything over. There's no way around it. Removing items, exact same deal. So now it should be pretty clear to you why stack 2 is so much worse than stack 1. Every time we're doing add or remove, there's a lot more work that has to go into stack 2 because we're doing everything from the beginning. Now, in evaluating the quality of our programs, we've only talked about 2 metrics. The first is correctness. Does it work? Even in special weird cases, and does it handle errors when they come up? The second is design. Is it designed well? Is it well documented? If someone picks up your code, is it easy to understand and use? From what we've seen about the 2 different stack implementations, there's also another thing we can use to measure the quality of the code, and that's running time efficiency. And there's a lot of study that goes into how to assess this properly and also how to communicate this with other computer scientists, and you're going to see a lot of this in your CS career. Now, in terms of runtime, remember that for most algorithms, how quickly they run depends on how big the input is. As the input gets bigger or lists get larger, for example, you can expect an algorithm that runs on it to increase as well. So when we're talking about efficiency, we really care about a mathematical function of the amount of time an algorithm takes to run based on how big the input is. So something we might say is, t of n to denote the runtime of a function on input size of n. This doesn't necessarily mean it's going to be n. Now, how do you measure the runtime? You could use a tool like TimeIt, but there's a lot of factors that go into that. First off, my computer might be faster than yours or slower than yours, so comparing my results to your results might be very meaningless. I have a bunch of things running right now. Chrome is a particularly vicious creature for having a bunch of tabs open. Don't mind my little Reddit tab I had, for instance. How much stuff I have open may have affected how quick that stack was running. So, like Schrodinger's cat, even observing the runtime can affect the performance. This is I feel like no one understands this analogy properly. Ignore my Schrodinger comment. This is very misunderstood. Now, what about the basic number of steps an algorithm takes? This is something that's a little bit better, right? And we saw a little bit of this just from watching the way that Python tutor runs on things. We can look at, for instance, step 1 of 5. Now, granted, this isn't the end-all be-all of how many steps something takes to run. There are some things that get shortcut here, but that is a little bit better than looking at, seconds, for instance. So, for instance, do all basic operations take the same amount of time? What is a basic operation? Does it take as much time for me to add two numbers together as it does to multiply them? For example, according to Python Tutor, it would be the same time, but that's not necessarily actually the case. There's a lot that goes in. So this is where you hear the concept of big O. It is an arguably elegant way of characterizing the type of growth of the runtime of an element without worrying about little nitty-gritty details and implementation stuff, whether a for loop is faster than while loop, so on. Not that those things don't matter, because they do, but they're another level of detail that is probably arguably less important. Worrying about that kind of stuff is not as big of a deal compared to worrying about the growth rate that big O describes. When we're talking about big O properties, what we really mean is things like linear, quadratic, logarithmic, exponential growth. So when we see a loop through a loop like this, for each item in the list, do a thing. We know that the runtime is proportional to the length of the list. If the list is twice as long, we expect the thing will take twice as long time. So the runtime grows linearly with the length of the list. Thus we write the runtime is big O of n, where n is the length of the list. And this is, the straight line linear function, right? In CSC165 or CSC240, you may learn about the formal mathematical definition of big O notation. We do this in 236 as well. But it's not going to be covered too much in this course. Intuitively, big O notation allows us to analyze running time while ignoring two details. First, lower order terms and constants basically get chucked out. So if you look at 5n, n plus 10, 19n minus 10, 0.05n, we just group all of them together and say we don't care about constants, we don't care about multipliers, anything like that. They all have linear growth, and that's the thing that matters. Think about it this way. I guess it comes into the second point here. Running time on small inputs. The idea here is we don't really care about how fast your code runs when it's running on really, really small inputs. We care about what happens on big inputs. The idea here is that these n's that you see are gigantic numbers, like 10 million, 100 million, billions even. That's when we start to care about how long something actually takes to run. And so being able to see that, when you see that happen, these constants start to not make as much of a difference compared to the sheer scale of the actual inputs that you're seeing. Big O notation allows us to capture running time as the size is growing. So we say that big O deals with asymptotic runtime. As your inputs get huge and huge and huge, what does it look like in terms of how things run? If we just have our code up here, the time it runs is pretty much directly proportional to the size of the list. So, straight line. But maybe, for each item in the list, then for each other item in the list, do a thing, you might see it curves up instead, right? In terms of how long it takes to run everything. Now, these points mean that big O notation's not necessarily suitable for everything. For example, a sorting algorithm, merge sort, runs in big O of n times log n. Algorithm insertion sort runs in big O n squared. For small inputs, insertion sort is significantly faster. And sometimes the constants do matter. Even though another algorithm called quicksort is on average big O n log n, its constants are smaller than merge sort. And so typically in practice, even though mathematically speaking they're similar, quicksort may actually be quicker a fair number of the times. These are not observations captured by big O, but they are practical and may matter depending on your circumstances. So here's a really quick summary sheet of the different most common big O classes and how we describe them in English. So big O of log n, we say logarithmic. That's where the curve goes up and it slowly starts to decrease in slope over time. Big O of n, linear, it's just a straight line through. Quadratic and squared, so curves upwards. and exponential just skyrockets to the top real fast. And remember, when we say exponential growth, that's when the variable is in the exponent, not the base. So n squared quadratic, 2 to the n exponential. Remember that the constants aren't a big deal, so if this was a 3 instead of a 2, we wouldn't treat it really that differently. And similarly, if this was 3 to the n versus 2 to the n, they pretty much are treated near the same. Now, there's also a nice mathematical intuition that describes these as well. So suppose you have an algorithm that has a running time of n0 when given an input size n, and running time n1 when the input size doubles. We can characterize the rates of the growth in terms of relationship between n0 and n1. So if your algorithm has big O of log n, then when you double the input size, it adds basically a constant to the running time of the runtime on the smaller input. If it's linear, then the runtime for when you double the size of the input is double what the runtime was. So n0 had some amount of time. If you double the size of the input, then n1, which is going to be double the input size, is double the time. For something like n squared, your original input, when it doubles in size, means that the runtime is going to go 4 times in size, the square of it, right? And then exponentially speaking, you take the runtime on the original input and square that, and then that's what your new runtime is going to be. Now, there's one more use of big O notation that we require, which is the use of a function where the growth does not depend on the input. So consider the constant function f of n is 10. It's literally the number 10. Doesn't matter what n is, it always gives you 10. So we say this has constant asymptotic behavior, and we rate this as big O of 1. Once again, remember, the actual value of the constant doesn't matter, it's a constant. In the context of running time, we say a particular function or method runs in constant time to say how fast it runs doesn't matter what the input is. For example, our above discussion about index lookup in array-based Python lists can be summarized by saying it's a constant time operation. Looking up an element in a list given its index takes time that does not depend on the length of the list or the value of I. You can do it no matter how big the list happens to be.